Good afternoon, dear participants of the conference. My name is Nastasia Varabyeva. I'm a PhD student at the Institute of Bioorganic Chemistry. I would like to present my work, nickel PHOTOREDOX catalyzed ARYLATION and alkenylation of cyclopropanols. Today, PHOTOREDOX catalyzed reactions are a promising area of research. Their main advantage is the generation of intermediate reactive radicals under mild conditions. One of the types of such reaction is nickel PHOTOREDOX catalyzed cross coupling, which has become widespread over the past 8 years. In this reaction, two catalytic cycles are combined, the PHOTOREDOX catalytic cycle and the nickel catalytic cycle. The radical particle formed in the PHOTOREDOX catalytic cycle is then involved in the nickel catalytic cycle, where it is cross-coupled with the coupling partner. Readily available chemical compounds, carboxylic acids and their derivatives, alkyl trifluoroborates, bis-catecholate-silicates, dihydropyridines, alkyl halides, sulfonate salts, Katritsky salts, alkanes, and others are used as radical precursors in nickel PHOTOREDOX catalyzed reactions. New methods for the construction of CC bond are in wide demand in the synthesis of natural compounds. For example, in our institute, research is being carried out to develop a total synthesis of sphingositol A. Subunit 1 in its synthesis was obtained by the cross-coupling reaction of vinyl triflate 2 and trifluoroborate 3, obtained in 3 steps from cyclopropanol 4. This strategy requires a large number of stages. Therefore, our research group set out to develop a method for construction of CC bond, which would allow direct cross-coupling of cyclopropanol 4 with vinyl triflate 2. Cyclopropanols, which are a source of beta-cat radicals, can undergo PHOTOREDOX nickel dual catalyzed reaction to provide beta substituting ketones. However, the scope of cyclopropanols that were engaged in this coupling is rather narrow. In fact, only one cyclopropanol substrate containing PMP group was reported to undergo such a reaction. In the course of the study, it was found that the presence of titanium isopropoxide as an additive overcome the limitations in the reaction scope. The oxidation potential of cyclopropanols is 1.7 volts. Therefore, strong oxidizing agents are required for the one-electron oxidation. Reduction potential of the excited photocatalyst commonly used in nickel PHOTOREDOX catalyzed reactions lies between 0.8 and 1.4 volts. This photocatalyst cannot lead to the generation of an oxycyclopropyl radical, but they can catalyze the cross-coupling stage because of the high ground state redox potential. Our attempts to use photoexcited actinium salts with high reduction potential in the ring opening relation were unsuccessful because it does not catalyze the cross-coupling stage. Nevertheless, we found that addition of titanium isopropoxide to the reaction mixture enables the reaction even when phosphozapine is employed as a photocatalyst. The first task was to optimize the reaction conditions. The highest yield in the ARYLATION was achieved when the reaction was performed in acetone in the presence of the photocatalyst phosphozapine, the nickel chloride bipyridine complex, potassium carbonate as a base, and titanium isopropoxide as an additive. Then we tested other solvents, ligands, bases, and additives, but the yield of product decreases compared to that under the standard conditions. Having established the optimal conditions for this nickel-photoredox relation, we focused our attention on the scope of the aryl bromides. Aryl bromides with donor or acceptor functional groups, as well as an orthos substituent reacted with cyclopropanol, giving desired beta aryl ketones in 46-58% yields. Silylated hydroxyl alkenyl diethyl acetyl units in the cyclopropanol were tolerated. Next, cross-coupling of cyclopropanols with vinyl halides was investigated. The reaction between cyclopropanol and 2-brom alkanes provided ketones 14A and 14B in 84 and 55% yields, respectively. Alkenylation of cyclopropanol with vinyl triflate also proceeded efficiently, given beta-cyclohexenyl ketone 14C. Beta-gamma unsaturated ketones 14D and 14E from 2-alkyl substituted vinyl bromides were isolated in 45 and 46% yields, respectively. A decrease in isomeric purity was in the course of the reaction, affording product 14G and 14H, which be the alkane unit conjugated with an electron-rich aromatic ring. Ketone product 14F with the unsubstituted benzene ring was obtained as a single Y isomer. Diverse cyclopropanols with hydroxyl, hydroxyl, alkenyl diethyl units, as well as alpha stereocenter in the side chain were tolerated. Arylation and alkylation of 1,2-D substituted cyclopropanols in 41-64% yields. The result of these experiments makes it possible to carry out an anti-selective transformation in the future due to the use of chiral ligands. Based on the experiments, the following reaction mechanism was proposed. The reaction begins with the oxidative addition of aryl bromide to nickel 0 particle with the formation of nickel 2 complex 17, which undergoes one electron oxidation by photoexcited phosphate-APN and the ligand exchange with titanium alkoxide 18, which gives the intermediate nickel 319. Next, the nickel O bond in 19 would break, providing nickel 2 complex and oxycyclopropyl radical 21. Ring opening of 21 will give beta ket radical 22, which would further react with 20 to afford nickel 3 complex 23. A reductive elimination from 23 lead to coupling product 24 and nickel 1 spices 25, reduction of which would close the catalytic cycle. Thus, in the course of work, a general approach to beta-aryl and beta-alkenyl ketones from cyclopropanols and aryl or alkenyl bromides or triflates was developed. It was found that the presence of titanium isopropoxide enables the reaction. The cross-coupling is compatible with functional groups, including an unprotected hydroxyl, and proceeds under conditions mild enough for the preparation of an antimerically pure ketones bearing a sensitive alpha stereocenter. Dear participants of the conference, that's all. The authors are grateful for the financial support from the Belarusian Foundation of Fundamental Research and Alexey Yantsevich. Thank you for the attention.
Thank you for your presentation. Any questions? Yes.
Alexander Vyacheslamovich. Yes, Susanna.
Thank you for this presentation. This is a very nice results presented, many results, I would say. And I would say that many things should be have to be planned very carefully for such synthesis. So could you tell me which conditions were most demanding for the synthesis and which conditions were most successful?
The most successful condition is when we use 4-zeta-APN as a photocatalyst, nickel chloride bipyridine complex for ARYLATION. But for ALKENYLATION, the most successful was neocuprine ligand. Also, in this reaction, the most important role play titanium isopropoxide because it enables the reaction. Reaction was performed in acetone, and we also use potassium carbonate as a base.
And what are these 2% for example on 14P? What are two kind of percents? 55 and 100%. What are these means?
55% yield of the product.
And what is 100%? What is EE?
For obtain this substance, we use neocuprine ligand, 2%.
Thank you very much. Thank you.
Thank you, Susanna. Any questions? Okay.
Thank you for your presentation. Tell me please two things. What is the procedure of isolation of the products? The first question. And the second one, the yield of the reaction is about 50%, 60%. Do you analyze another product of the reactions? What they are? Do you know?
I'm sorry, I can't understand questions. Should you please speak down?
Oh, okay. The first question is, what procedure for isolation of your compounds? How do you isolate them from the reaction mixture?
Okay, I understand.
Okay.
We isolate our compound. For isolate, we use a solution of hydrochloric acid, and then we dried organic lies, filter it and evaporate the solvent, and then we performed the column chromatography.
Okay. And the question is the yield of the procedure. I can see it's about 50, in most cases, 50, 60%.
Yes.
What's the rest? Do you analyze what the rest of the products? It was a starting material or something else. Do you analyze that?
No, we not analyze. Maybe reaction. Maybe in the reaction mixture was cyclopropanol, little amount of cyclopropanol.
Okay, I see. Because it's if you wish to make conclusion about the mechanism, you have to analyze your minor products. So I would recommend you to check your scheme and to look in the inside of the minor products of the reaction. Okay, thank you very much.